Let's look at your answers to question 3. In 3.1 it says, use the expansion for cos 2 beta to write expressions for, firstly, the cos of beta, and secondly, the sine of beta. So let's have a look at this. We know that the cos of 2 beta can be written in one of 3 ways. It can be written either as the cos squared of beta minus the sine squared of beta, or it can be written as twice the cos squared of beta less 1, or as 1 minus twice the sine squared of beta. Now in A, we have to write an expression for the cos of beta. So the cos of beta. So we're going to use the second option here. In other words, the cos expansion for 2 beta that contains only cos in it. So then we know that twice the cos squared of beta less 1 is equal to the cos of 2 beta. Now we merely make the cos of beta on the left-hand side here the subject of the formula. So we can first take the negative 1 to the right-hand side. Now we're going to divide by 2. So the right-hand side over 2. And finally, we're going to take the square root on the right-hand side. So it's going to be plus or minus the square root of the right-hand side. So we've now written an expression for the cos of beta by using the cos of 2 beta. Then in B, we have to write an expression for the sine of beta. So in this case, we're going to use the third option here. In other words, we're going to use the expansion of cos 2 beta that contains only sine in it. So then we know that 1 minus twice the sine squared of beta equals the cos of 2 beta. Once again, we're going to make sine beta, or in this case, we're going to make sine beta the subject. We can first take the 1 to the other side. Now we're going to divide by negative 2. Now, we could divide the negative into the numerator. Then we're going to get plus 1. A minus divided by minus is a plus. So plus 1 minus cos 2 beta. So basically 1 minus cos 2 beta over 2. So we basically divided the negative into the numerator and then just switched around the terms. Then finally, we're going to take the square root again on the right-hand side. So it's going to be plus or minus the square root of the right-hand side. Then coming to 3.2, we have to use the expansion for sine 2a to write down an expression for the sine of a times the cos of a. Of course, we know that the sine of 2a is twice the sine of a times the cos of a. And we want an expression for the sine of A times the cos of A. So we merely divide the 2 into the left-hand side over here. So then the sine of A times the cos of A is equal to the sine of 2A divided by 2. Let's look at 3.3. We have to simplify this expression to a single trig ratio. So we have the 4 times the sine of theta times the cos of theta. And this is all over cos squared theta less sine squared theta. Now, the denominator here, of course, is the expansion for cos 2 theta. Remember, this is one of the 3 expansions for cos 2 theta. So we can reduce it to the cos of 2 theta. If you look at the top, it almost looks like the expansion of sine 2 theta, except that we have a 4 here. Remember that the sine of 2 theta is twice the sine of theta times the cos of theta. Here, however, we have 4 times the sine of theta times the cos of theta. We can rewrite the 4 as 2 times 2. So 2 times twice the sine of theta times the cos of theta. Then what we have in the brackets here, of course, is the sine of 2 theta. So then the top we can rewrite as we said twice sine theta times cos theta is basically sine 2 theta. Then in the denominator we have cos 2 theta. So we can rewrite this fraction as twice or 2 times the sine of theta, the sine of 2 theta rather, over the cos of 2 theta. And this is a quotient identity. Remember, sine over cos is tan. So this reduces to twice or 2 times the tan of 2 theta. So in question 4, we are given 2 equations for P and Q respectively. And we have to find the trig ratios given below, in other words cos 2 alpha and tan alpha in terms of P and or Q. So let's have a look at this. We know that the cos of 2 alpha can be written as a cos squared of alpha minus a sine squared of alpha. Now, let's have a closer look at P and Q. When we multiply P and Q together, we get a difference of squares. In other words, P times Q, or PQ, will be cos alpha. So cos alpha plus sine alpha multiplied by cos alpha minus sine alpha. And as we said, this is a difference of squares. So we square the first term minus, and we square the second term. Of course, this is the same as what we have here in this equation. In other words, cos squared alpha less sine squared alpha is cos 2 alpha. So then we can conclude that the cos of 2 alpha is P times Q, or PQ. Let's look at B. We have to write the tan of alpha in terms of P and Q. Now, we're going to start by writing tan alpha as the sine of alpha over the cos of alpha. The reason that we want to do this using the quotient identity is because both P and Q are given strictly in terms of sine and cos. Now we simply have to find sine alpha and cos alpha in terms of P and Q. Now something to notice here, when we add P and Q, so when we take P plus Q, the positive sine alpha here will cancel with the negative sine alpha over here. And we'll be left with cos alpha plus cos alpha. In other words, we'll be left with twice the cos of alpha. So let's write that down. So P plus Q gives twice the cos of alpha. Now we make cos alpha the subject of the formula. So cos alpha will be P plus Q over 2. So we can replace cos alpha here with P plus Q over 2. Now similarly, when we subtract Q from P, so P minus Q, the cos alpha here will cancel with the cos alpha over here. And we'll be left with sine alpha minus negative sine alpha. In other words, sine alpha plus sine alpha, or 2 sine alpha. So P plus Q, or rather P minus Q, will give us 2 sine of alpha. Once again, we can make sine alpha the subject. So it's P minus Q divided by 2. Now we can rewrite this fraction. So then the tan of alpha will be the sine of alpha, which is P minus Q over 2, divided by cos alpha, which is P plus Q over 2. We're dividing a fraction by a fraction, so we can multiply the numerator by the inverse of the denominator. Of course, the 2's will cancel here, and we're left with P minus Q over P plus Q. Let's look at 4.2. It says simplify P over 2Q minus Q over 2P to a single trig ratio of alpha. Now, we can start by writing these two fractions as one fraction. So we can find the LCD. The LCD, of course, is 2PQ. Then 2Q into 2PQ. P remains times the numerator, so P squared. And 2P into 2PQ, Q remains times the numerator, which is Q squared. Now we're going to bring in the sine and cos of alpha. Now, in order to reserve space, I'm going to write cos alpha as C alpha, or C, and sine alpha as S. So P squared, we know that P is cos alpha plus sine alpha. So then P squared will be C plus S all squared. And Q squared will be C minus S all squared. Remember that Q is cos alpha minus sine alpha. This is all over 2pq. So 2 and p we said is c plus s. Q is c minus s. Now we're going to square out in the numerator. So c plus s all squared. So it's a first term squared plus, so this sign, plus twice the first term times the second term. So 2 times c times s, then plus the second term squared. Then we keep brackets when we square out the second set of brackets here because of the minus in front. So then it's a first term squared, the sign, the first term times the second term times 2, so 2cs, plus the second term squared. Then in a denominator we have a difference of squares. So it's simply the first term squared, so c squared, minus the second term squared. We can continue to simplify. So I'm just going to rewrite the first three terms in the numerator. We can multiply this minus into the brackets here. And I'm going to leave the denominator like this for now. Now, in a numerator, there are terms that cancel. So c squared here with negative c squared over here, s squared with negative s squared here. Now we're left with twice cs plus twice cs in the numerator. And in the denominator, we're left with 2 into c squared minus s squared. Of course, in the numerator, these two terms can add up to 4cs. And this is all over 2 into c squared minus s squared. 2 can go into 4 here. And we're left with cs on top. Of course, 2 into 4 twice. So 2cs on top. And we said that c is cos alpha and s is sine alpha. Then in the denominator, we have c squared, which is cos squared alpha, minus s squared, so sine squared alpha. Now, if you look carefully at the numerator, this is nothing but the expansion of sine 2 alpha. So the numerator is sine 2 alpha. The denominator, of course, is nothing but cos 2 alpha. Remember that cos squared alpha minus sine squared alpha is one of the 3 expansions of cos 2 alpha. And we know that sine over cos is tan, so this ratio reduces to tan of 2 alpha. In 5.1, we are given that sine x equals cos 2x minus 1. And we need to show that 2 sine squared x plus sine x equals 0. So we have to use the first equation to prove the second one with. So let's write down the first equation. Now, important to note that we have a cos in the first equation, but there's no cos in the second equation. So we're going to use one of the three expansions for cos 2x and write cos 2x in terms of sine only. We know that cos 2x is 1 minus 2 sine squared x. Remember that this is one of the three expansions for cos 2x. Now the 1 here cancels with a negative 1, and we're left with negative 2 sine squared x on the right hand side. We need to show that 2 sine squared x plus sine x is 0. So we bring the right hand side across to the left hand side. And we basically have proved the identity or the equation. Then in 5.2, we are given that sin x plus cos x equals the square root of 1 plus k. And we have to find k as a single trig ratio. So let's start with what we are given. Now, we need to isolate k. So the first thing that we can do is to square both sides to get rid of the square root here. So squaring the left-hand side, it's a first term squared. Then this sign, so a plus. Then the first term times the second term times 2. Then it's the second term squared. And then on the right hand side, when we square the right hand side, the square root drops. So it's 1 plus k. Now, if you look carefully on the left hand side, we have sine squared plus cos squared, which is a square's identity, and it's equal to 1. Then 2 sin x times cos x is expansion for sine 2x. So it's sine 2x. The ones cancel on both sides. And we're left with k equal to sine 2x. And now we've answered the question because we needed to put k or write down k as a single trig ratio. And here we have k is equal to sine 2x. Then in 5.3, we are given that x plus 1 over x equals 3 cos a, and also that x squared plus 1 over x squared is 2. And we have to find the value of cos 2a without a calculator. So we're given that x plus 1 over x equals 3 cos a. Here we can square both sides. The reason why we're squaring both sides is that we see that we have x squared plus 1 over x squared in the second equation here. So squaring out the left-hand side. So it's a first term squared. Then the sign, so a plus. Then it's the first term times the second term times 2. So if we take the first term times the second term, so it's x times 1 over x, and then multiplied by 2 we see that the x's cancel here, and we're left with 2. So the first term times the second term times 2 is equal to 2. Then we square the second term, so it's 1 over x squared. Then on the right-hand side, squaring the right-hand side gives 9 cos squared a. So if you look carefully at the left-hand side, we have x squared plus 1 over x squared, which we know is equal to 2. So then the left-hand side will be 2 plus 2. So x squared plus 1 over x squared is 2, and then we're adding this 2. So rearranging this equation, 2 plus 2 of course is 4. And we now have a value for cos squared a when we divide the 9 into the right-hand side. We are asked to determine a value for cos 2a. So we're going to use a double angle expansion for cos 2a in terms of cos squared a. We know that cos 2a is 2 cos squared a minus 1. And we have a value for cos squared a. It's 4 over 9. So we can fill it in here. So it's 2 times 4 over 9 minus 1. We can simplify this. 2 times 4 is 8. So it's 8 over 9 minus 1. And we could do this on a calculator. 8 over 9 minus 1 is minus 1 over 9. And now we have a value for cos 2a, which is what we were asked to do. So in 6.1, we need to show that 1 minus cos 2q is equal to 2 sine squared q. Now, we're going to start with the left-hand side, but before we do that, just to note that the left-hand side contains cos and the right-hand side contains sine, but no cos. So let's start with the left-hand side. It's 1 minus cos 2q. And we need to get rid of the cos because the right-hand side doesn't have a cos in it. So we're going to use one of the 3 expansions for cos 2q. So a double expansion or double angle expansion. And more specifically, we're going to use the one that involves only sine. We know that cos 2q is 1 minus 2 sine squared q. And of course we need brackets here because of the negative that we have here. Now we can multiply the negative into the brackets. And of course the ones cancel. And we're left with 2 sine squared q. And this of course is equal to the right-hand side. So we have proved the identity. Then in 6.2, we are given that the sum of angles P, Q and R is 180 degrees. And in A, we need to show that the sine of 2R is negative the sine of 2P plus 2Q. So let's start with the left-hand side. It's equal to the sine of 2r. Now, what's important to note, in the identity that we need to prove, the left-hand side contains r only, whereas the right-hand side contains p and q, but no r. So we can use this equation here to write r in terms of p and q. So we know that r, so angle r, will equal 180 degrees minus p plus q. Now we can go back to the left-hand side. And we basically can replace r with 180 degrees minus p plus q. We can multiply the 2 into the square brackets. So it's 2 times 180 minus 2 times the round brackets. Now we can use quadrant rules. We know that 360 minus theta. So we can regard this 2 into p plus q as theta. We know that 360 minus theta is the fourth quadrant, and sine is negative in the fourth quadrant. So it's negative sine, and sine of 360 minus theta is negative sine of theta. In this case, of course, theta is 2 into p plus q. So it's negative sine of 2 into p plus q. The last step here is to multiply the 2 into the round brackets. And this is equal to the right-hand side. Then in 6.2b, it says, hence, show that this equation is true. Now, the word hence tells us that we must use the previous result. So let's start by writing down the left-hand side of what we need to prove. So it's sine of 2p plus a sine of 2q plus a sine of 2r. Now, we're going to replace the sine of 2r with the right-hand side of the previous identity. So, the left-hand side and sine 2r we're going to replace with negative sine of 2p plus 2q. Now we're going to use the sign expansion for a plus b. Now remember that the sine of a plus b is a sine of a times the cos of b plus the cos of a times the sine of b. So here it's a sine of 2p times the cos of 2q plus the cos of 2p times the sine of 2q. We can multiply this negative into the square brackets here. Now we see that we've got common factors. We have the sine of 2p here, as well as over here, and we have the sine of 2q here, as well as over here. So we can take out these common factors. Let's start with the sine of 2p. The sine of 2p into the sine of 2p once, then this sine. And here, when we take out the sine of 2p, we're left with a cos of 2q. Now we can take out the sine of 2q, so it's a plus. The sine of 2q into the sine of 2q once. Then this sine, so a minus. And here we are left with the cos of 2p. Now, let's go back to the question. We want to know what to do with this 1 minus cos 2q and 1 minus cos 2p. If you look back on 6.1, we see that 1 minus the cos of 2q is 2 times the sine squared of q. Similarly, 1 minus the cos of 2p, using the same result, is equal to 2 times the sine squared of p. Now we can use the double angle expansion for sine of 2a. Remember, the sine of 2a is twice the sine of a times the cos of a. So the sine of 2p here is twice the sine of p times the cos of p. Similarly, the sine of 2q is twice the sine of q times the cos of q. We can simplify. 2 times 2 is 4 here. And here we have 2 times 2 as well. Now we have more common factors. We have a 4 as a common factor. We also have a sine of p as a common factor over here. And we have a sine of q. So we can take out this common factor, 4 times the sine of p times the sine of q. What we have left here, when we take out this common factor, is the cos of p times the sine of q. I'm going to write it as the sine of q times the cos of p. Then this plus. And here, what we are left with, of course, when we take out 4 sine p sine q, the sine q will cancel here. And we're left with the cos of q times the sine of p. Now, if you look carefully at what's in the square brackets, this is the sine expansion for p plus q. Now, of course, p plus q is 180 minus r, using this equation here. So it's a sine then, the sine of p plus q is the sine of 180 minus r. Now, using quadrant rules, the sine of 180 minus theta is the sine of theta. So this is the sine of r. And now we have proved the right-hand side. Then in 6.3, it says if tan 2 alpha is equal to k, evaluate this expression in terms of k. So let's start with the expression. We can start by taking out a common factor of 2 in the numerator. Then the denominator is actually the expansion for sine 2 alpha. In other words, the double angle expansion. Then 2 cos squared alpha minus 1 is the expansion, or one of the expansions for cos 2 alpha. Now, remember that we have to write this expression in terms of k. So I'm going to rewrite what we have over here slightly. So it's 2 times cos 2 alpha over sine 2 alpha. We were also told that the tan of 2 alpha is equal to k. Now, bearing that in mind, I'm going to write cos 2 alpha over sine 2 alpha as sine 2 alpha over cos 2 alpha all to the negative 1. Now, sine 2 alpha over cos 2 alpha, of course, is tan 2 alpha. This is using the quotient identity. So it's tan 2 alpha to the negative 1. But tan 2 alpha is equal to k. So it's 2 times k to the negative 1. And using the laws of exponents, k to the negative 1 is 1 over k. And then 2 times 1 over k is 2 over k. So we have written the expression in terms of k. So let's look at the last question here, in other words 7.2.3. It says here, show that sine theta is a solution to this cubic equation. Now, what does that mean? It means that sine theta must satisfy this equation. In other words, we actually have to prove, so require to prove, that when we substitute sine theta in for x, it satisfies the equation and we get 0. So we need to prove that 8 sine squared theta minus 4 sine theta plus 1 equals 0. So here we just plugged in sine theta for x. And of course this should be sine cubed, not sine squared. Now, the important thing to note here is that this equation is entirely in terms of sine only. And we're actually going to use the result from 7.2.2, in other words, this identity, to prove this with. So let's write it down. On the right hand side, we have 4 cos squared, or rather 4 cos 2 theta. But as we said, this equation here is entirely in terms of sine only. So I'm going to use a double angle expansion to write cos 2 theta in terms of sine. So we know that cos 2 theta is 1 minus twice the sine squared of theta. Now we just manipulate this so we can multiply the 4 into the brackets. We can get rid of the sine theta here, this fraction, by multiplying through by sine theta. On the left hand side, we're going to end up with 1. And then 4 times sine theta. And then this, of course, times sine theta will give us sine cubed theta. Now we just bring everything to the left-hand side. And as you can see that here we have proved this identity, that this holds.